All right, so one of the most effective ways to determine the rate law for any chemical reaction is using something called the method of initial rates. So why don't we go ahead and just look at a very simple reaction here of A going to P. And what you can do in a laboratory scenario is you can make a table of the concentration of A and then measure what we call its initial rate. Molar per second. And how would you measure this initial rate? You could be looking for things like color changes in solution. So if P is, let's say, you have a colorless solution, and then as the A is consumed, it makes P, which is yellow. You could use a spectrometer to measure how yellow the solution is. It goes over to Beer's law, and that's one way we can certainly do it. So colorimetric, or what we call following by color, is one of the best ways to do it. All right, so what we can do here is look at the concentration of A, and of course the brackets indicate that we're talking about molar, and we have an initial rate of 0.015 molar per second. If we increase the concentration in a separate experiment, all right, so what I'm going to do is now run the experiment again at a concentration of 0.2. I'm going to follow that color change with my spectrometer, and I'm going to see that color change happened within a certain amount of time, and that change in concentration per unit time I found to be 0.03. And then I go up to 0.4 and I get to 0.060. All right. So I've got a data table here. And what this allows me to do now is look at how it changes in concentration and what effect that had on the initial rate, that very, very, very beginning of the slope. All right. So that's convenient because at the very, very, very beginning of the reaction, I should have a straight line because the reaction is happening so quickly. So again, if we look at this plot of A as a function of T, at the very beginning, remember, it's going to be what we call linear. But as it goes on, it slows down. Oh, sorry, that was pretty sloppy. It slows down and becomes non-linear. But if I look just here at the very, very beginning, it's a straight line. So I can just go ahead and look at the change in concentration and how it changed that rate very quickly. All right. And the degree of which that changed in a linear fashion gives me the order of reaction. So in other words, what happens between here and here? All right. My concentrations did what? They doubled. All right. And then between here and here, 0.2 to 0.4, my concentrations also doubled. All right. So I've got X2, I doubled them. But look at my initial rates. What happened here? I went from 0.015 to 0.03. Well, that doubled. And then here, from 0.3 to 0.6, that also doubled. All right. So what can I say? I can say doubling concentration resulted, let me be more careful, doubling concentration of A resulted in doubling of reaction rate. This is consistent with first order behavior. Right. This often confuses students because they see doubling and they want to just jump to second order because doubling has a factor of 2 and second order has a 2. But that's not the case. The second order has to do with an exponent. All right. So let me clarify. If it's going to be first order in A, I can write a first order rate expression for A. All right. And let's just go ahead and put that exponent of 1 there to help us out. If I plug in a value of 1 for A, I get a rate. If I plug in a value of 2 for A, I get double that rate. How do I know that? There's the data right here. So going from 0.1 to 0.2, that rate did what? Doubled. Doubled the concentration, doubled the rate. Okay? So if I double this guy, that means I'm going to double this guy. That makes sense for a first order. Now, what the heck's K doing? Don't worry about it. It's a constant. All right? So if you do this at constant temperature, it's just going to sit out there and be a constant. Okay? So this is consistent with first order behavior. So what I'm going to say is doubling concentration of A and results in a doubling of the reaction rate. That's a first order in A. All right? And since our reaction only has one reactant, it's not only first order in A, but the reaction is first order overall. Okay? So it's going to be first order in A, first order overall. All right, let's look at a two-component reaction. How do you deal with that? So if we take A plus B, and this goes to P, I need to measure the concentrations of A and B, and we're going to have the rate initial. So this is V for velocity, right? You'll see that quite often, and I means that initial rate. So they did it at a very, very short interval at the beginning of the reaction, right? And that's in molar per second. All right, so I'm going to run my reaction with 0.1 molar A in experiment 1, 0.1 molar A in experiment 2, and 0.20 molar in experiment 3. Experiment 1, I'm going to have 0.1 molar in B, 0.2 molar in B in experiment 2, and 0.10 B in experiment 3. All right, and then I measure the rates of these reactions at 0.4, 1.60, and 0.80. All right. So this is where you have to be a good little scientist and recognize if you're going to change one thing and see its effect, the other thing you better leave alone. All right? So what I mean by that, I had to be smart when I was changing my concentrations. For A, I went from here to here, and that concentration remained constant. All right? That's because I wanted to see what the effect of the rate of reaction was by varying B. Okay? So I did vary B from experiment 1 to experiment 2. And I happen to double it here. All right? Okay, what happened to the rate in that change? The rate went from 0.4 to 1.6, so it went up by a factor of 4. All right? Went up by a factor of 4. Now, let's compare some other experiments. Where did A change? A changed over here, right? And B, thankfully, remained constant, all right? What happened over here? The rate did indeed change. So my question is, on my green line, how did A change? Changed by a factor of 2, going from experiment 1 to experiment 3. How did the rate change going from experiment 1 to experiment 2? So 0.4 to 0.8, that also doubled. Okay? So let's see. B, which is in blue, change. Doubling of B gave a quadrupling of the rate. Doubling of A gave us a doubling of the rate. All right, so let's go debrief here. So when we doubled the concentration of B, the rate went up by a factor of 4. A, we doubled A, and we went up by here. Okay? So this is first order behavior. doubling concentration results in a doubling of rate. Okay, we saw that in the previous expression problem. What happens when you double and it quadruples? That is something that we call second order behavior. All right, second order behavior. So why is that second order behavior? So let's pretend B exists by itself in this chemical reaction. All right, and we're going to say the concentration of B was 2 molar at the beginning, or experiment 1, and it was 4 molar in experiment 2. Now we're making something up completely different. All right, and let's say K is equal to 1 to make it easy. What happens in experiment 1? K is equal to 1, so it's just going to be a 1 out here. B is 2, and we square it. So 2 squared is equal to 4. All right. So think about that. All right. We just got a number 4 there in experiment 1. What happens in experiment 2? We increased our concentration of 4. 4 squared is equal to what? 16. So notice how we did what? We doubled the concentration from 2 to 4. What happened to the rate? The rate did what? 4 to 16 is a increase by a factor of 4. All right? So that's how we rationalize that it's second order. So now we can go back and look at these numbers here. All right? We say it's what? Second order in B, first order in A. All right? So now we can write the rate law. The rate law is going to be K. That's always the case. All right, the rate is equal to K, whatever that rate constant is. And actually, we can calculate it, and we'll talk about how to do that momentarily. But the rate constant is K. Then we had A. A was first order, all right? Then we had B. B was second order, so we need to put our exponent of 2 there, and you're done. You just got the rate law written for that reaction. So it's first order in A, second order in B, and what is the rate of reaction overall? Or sorry, the order of reaction overall? Well, 2 plus 1 is 3, so it's third order overall. All right? Okay. So we don't always deal with A's and B's and pretty numbers. All right? What we actually have is real chemicals and real data. So what I want to do now is look at a real chemical reaction of NO2 gas plus carbon monoxide gas going to NO gas plus CO2 gas. All right, so we have a gas phase reaction here, and the experimenters ran 4 different experiments where they monitored the concentration of NO2, and they monitored the concentration of carbon monoxide, and they looked at the initial rate in molar per second. All right? All right, so I'm going to go ahead and fill in this data table. All right, so now we have our data table filled in, and we're going to go ahead and investigate where experiments were changed in one and remained constant in another. All right, so let's go looking through NO2. All right, so this will be this column here, and we're going to do it with green. All right, so in experiment 1 to 2, it looks like we changed the concentration. So let's look over at the third column, which is the carbon monoxide. Did we change the concentration there? And the answer is no. All right, So this would be a good experiment to look at. All right, so going from 0.1 to 0.2, we would say that concentration doubled. All right. And then going over here to see what happened to the rate. So it went from 0.0021 to 0.0082. All right. So some of you may not be as comfortable doing some of this math in your head. All right. So what you could simply do is just divide the increased number, 0.0082, and divide it by 0.0021. All right. You get it pretty darn close to 4. All right. It comes out to 3.91. You can go ahead and round that up to a factor of 4. All right. Because experimental data isn't always going to be absolutely perfect. All right. So we have times 4 there. All right. Let's go look at the carbon monoxide change and see if we can find one there. Okay, obviously it doesn't change between experiments 1 and 2, but it does change between experiment 1 and 3. However, it looks like my NO2 is also increasing, so I can't use that. All right. What about between 2 and 3? That'll work. Okay, because it changes from 2 to 3, but the NO2 concentration stays the same. So that's nice. Okay, so here it does what? Goes up by a factor of 2. And here, from 0.0082 to 0.0083, I would say that doesn't change. All right, that's almost identical. So when it doesn't change, that's a factor of 1. All right. So my question is, does the concentration of CO affect the rate of reaction? Clearly not. So what scenario do we have when a reaction concentration changes but the rate of reaction does not change? That's 0 order. All right? So let's go ahead and answer our questions real quick. In case of NO2, which is in green, doubling results in quadrupling of rate. So what would you tell me the order is for NO2? Second order. All right. What would you tell me the rate of reaction with respect to carbon monoxide is? Doubling it does not change the rate of reaction, so this is 0th. All right. So it's 0th order in carbon monoxide, second order in NO2. So let's go ahead and write this rate law. Without even thinking about it, you can write that. All right, rate is equal to K. NO2, we knew was second order. And carbon monoxide, CO, was 0th order. When you have 0th order, it's kind of weird, but you can actually drop it out of the equation if you wanted. Right, because anything to the 0th power is equal to 1, all right? So either expression is acceptable, all right? Now, I can ask a follow-up, or take this a bit further, I guess I should say. Calculate the value of K. In other words, calculate the rate constant for me, right? We've just been talking about it's just some number, but you now have the ability to calculate that number, all right? How do you do it? Do you know what the rate is? Well, yeah. I can pick any one of these experiments and pick its rate, all right? But whatever rate I choose, I better use the following concentrations. So to make life easy, just pick experiment 1 and plug in those numbers into the rate law and solve for K. All right, so let's go ahead and do that. Rate equal to K, concentration of NO2, squared, carbon monoxide to the 0th power. All right, and let's say experiment 1, our rate was 0.0021. And rate is always molar per second. Okay? Always, always, always. K, the units change depending on the order of reaction. All right? So we have to be careful with our units here. Okay? NO2 was 0.10 molar, and that was squared. And CO drops out. All right? Anything to the 0th power is just simply 1. Right? And the units are gone as well. Okay? So K now is equal to 0.0021 molar second divided by 0.01 molar squared. Okay, I went ahead and squared 0.1, and it gives me 0.01. And the units, okay, so molar gives me molar second. And I divided both sides by the 0.01 molar second. Or sorry, molar squared. So what ends up happening here is my unit of K. I just need to simply divide 0.0021 divided by 0.01. Guess I could have done that in my head. 0.21. And now what about the units? All right. Well, I have inverse seconds from the top, and one of those molars cancel with the square, so I have it divided by molar, so it's inverse molar on the bottom. I can't seem to. Right. Okay, so 0.21 molar to the -1, second to the -1. That's my value of K and my units of K as well. All right. So again, we mentioned that the rate constant is going to have different units for the overall reaction order. So if a reaction is 0th order overall, K has units of molar per second. First order overall, K has units of 1/seconds or inverse seconds. And second order overall, K has units of 1/molar second, or m to the -1, s to the -1, as we just saw. All right, so this is a handy little slide to make sure you're calculating your rate constants correctly, because those will be your units. All right, so this is the end of our discussion for the method of initial rates. All right. Next video on tomorrow, we're going to get into something called the integrated rate laws. All right, thank you very much.